So today we're going to be talking about vectors. I'm going to make the assumption that you don't know anything about vectors, although you may have done it in Extension 1 or Physics at this point, but it's easier if I just assume you've done nothing. I'll leave a link in the description in case you have done it, so you can just skip forward a little bit. So we need to know about two things, a scalar and a vector. So a scalar is just something that has a magnitude to it, like speed. I could just say I'm going down the highway at 100 kilometers an hour, but there's no sense of what direction I'm going. And that's where a vector comes in, because it has a magnitude and a direction associated to it. So now I would be talking about going 100 kilometers an hour south. In mathematics, we use a few different notations to represent vectors. The most common when things are written down in a book or on a computer, for instance, is going to be using boldface. So you can see here a bold A would represent a vector. But obviously when we're writing things down, even if I'm writing something down on the whiteboard or you're writing something down in your book, we can't write in boldface, so we need something else. So we'll normally put a tilde underneath it or an arrow over the top. For example here, the vector AB, it starts at A, finishes at B, so we'll write AB with an arrow over the top of it. And notice there we use capital letters. There's another vector here, CD. AB and CD are exactly the same length, they have the same magnitude, and they're both traveling in the same direction. The tail and the head are both pointing in exactly the same direction at the same angle. Therefore, they're really the same vector. They're just at different positions. So hence why we might call them a position vector. I can move them around wherever I want. And if I overlay them here, as you can see, they're the same vector. So the first thing we're going to want to do is look at how to do addition of vectors, because we can add them together just like we can add numbers together. And we're going to do it in two ways. The first way is a way, if you've done physics, you've seen it before, and it's the idea of a head-tail diagram. Remember, I've just said I can pick up vectors and move them wherever I want. So if I have a vector here, AB, and a vector CD, then I can pick up CD so that the tail of CD sits right on top of the head of AB. And by head and tail, I mean that the head is the arrowhead. We'll pick up the tail of CD and we'll pop it on the head of AB, and we've now got what we call a head-to-tail diagram, because we can travel from the tail of A to the head of B, tail of CD to the head of CD, and then we can produce a new vector from the tail of A to the head of B, and that's our new, what we call resultant vector, and that would be the addition. So that would be AB plus CD. In mathematics, the way we like to do things is using the idea of a parallelogram. So I've already talked about before when we had two vectors and they were really the same vector because they were the same size and pointing in the same direction. We can use that here to our advantage. So again, I've got a vector AB and a vector CD. This time though, I'm not going to put them head to tail. I'm going to pick up CD, so its tail is at exactly the same point as AB. It's going to form a vertex between those two. And then what we can do is we can basically make copies of them, move them around. So I can make a copy of AB here and I can move it somewhere else, and that somewhere else is going to be to the head of CD. And then I'm going to copy CD and I'm going to move it somewhere else, and that somewhere else is going to be to the head of AB. And you can see that I've formed a parallelogram now. And in fact, the addition of those two vectors, if we look carefully, adding AB and CD just means follow AB, follow CD. Where do I end up? And I end up, if I follow AB this way and CD this way, I end up at the point where the two arrows meet, the arrowheads meet. And if I join up the two tails to the two heads, then that's now my resultant vector, that's my addition. And you can see it's one of the diagonals of the parallelogram. So this parallelogram rule is a nice geometrical way of adding vectors. Before we do subtraction, we better talk about what a negative vector would be. So if I have the vector A, then taking the negative just flips the tail and the head around. So it's got exactly the same length, it's just pointing in the opposite direction. That's what we mean by a negative vector. The other thing we'll need is the zero vector. So the zero vector is a very special vector. It's a vector that has no magnitude, no direction. It's the only vector that has that property. So now I can define subtraction in terms of this negative and this 0 vector. Because I can say, okay, well, if I take the vector A and the vector negative A, they're exactly the same length, they're just pointing in different directions. So if I add them together, then I'm going to get the 0 vector. So I think I've got the vector A sitting here, and it's got tail and head. And then if I do a head to tail diagram, then I stick the tail of negative A on the head of A, and its head now is going to sit right where the tail of A is. In other words, I go up, I go down, I end up back where I started from. I've gone 0 distance. So I've now defined subtraction in terms of this negative vector. So in fact, subtraction, if I take two generic vectors A and B and I want to do A minus B, well, it's really the same thing as A plus negative B. And I can define geometrically what negative B means now, so I can do subtraction. And in fact, if we look carefully at our parallelogram rule, we can see a really nice geometric property occurring again. If I take, again, I've got the vectors A and B, and then I take negative B, then I can see that A minus B, or A plus negative B, produces as a resultant vector that other diagonal, which is really nice. So one diagonal of the parallelogram is A plus B, and the other diagonal is A minus B. So a really nice geometrical result that's going to prove really important, and you'll see lots of questions in exams and the HSC in particular revolving around this property. So let's consider multiplication now and see what it looks like geometrically. So we're going to consider two vectors OP and OQ, so they're coordinate vectors connected to the origin, and we're going to produce firstly a third vector, a rather special vector here, OA, which has a magnitude of 1. And that's chosen deliberately. And then we're going to produce the vector AP to form that triangle OAP. We're then going to produce a fourth vector, OR, and we're choosing it specifically so that it produces a similar triangle here, OQR. And when I say similar, hopefully you realize I mean similar to the triangle OAP. Now let's consider their magnitudes firstly. If we know anything about similar triangles, then we know that we've got some relationships between lengths. Specifically that length OR over OP is equal to OQ over OA. And we said that OA, remember we chose that specifically so it was 1, so that means it's really equal to OQ. Or rearranging things a little bit, the length of OR is equal to the length of OP times OQ. In other words, OR there is the magnitude of OR there is representing the product of the magnitudes of OP and OQ. And since they're similar triangles, if we look specifically at the angles, then we can see that the angle POA is the same as the angle QOR, and therefore the addition of the two angles for OP and OQ equals the angle AOR, which means we've basically proven that OR is in fact the product of OP and OQ, which is really nice. So similar triangles definitely help there. And what that's basically showing us geometrically then is that the product of two vectors produces a rotation as well as a scale. So they're similar triangles, not congruent triangles. So there is a stretching or compression that's happened as well. So rotation and a stretching or compression. If they happen to be congruent triangles, then there's no scale happening, it's just a rotation. Now you might be asking why we're learning about vectors here, we're talking about complex numbers, but have a think again back to modulus argument form. Yes, we can represent complex numbers in terms of a Cartesian system, x plus I, y, in terms of their real part and imaginary part, but we've also said that we can consider a complex number in terms of its distance from the origin and its rotation relative to the positive x-axis. So that's what r and theta are doing for us. And if you just think carefully about what we just said there, we're talking about a magnitude and a direction. So we can in fact represent complex numbers as a vector, which means everything we've just talked about suddenly works. We can use the parallelogram rule to work out additions and subtractions, and we can think of multiplications geometrically in terms of rotations and scalings of vectors. Another important result is called the triangle inequality. So let's suppose we have a triangle in the Argand plane, OAB, where OA is going to represent the complex number W, AB is going to represent the complex number Z, and therefore OB there must represent the complex number Z plus W. Now, thinking about triangles, it's rather obvious that the length of those two sides, OA and AB, has to be greater than the length of OB. There's a kink in it. It bends, and when I flatten that out, it would be longer than that side OB. So thinking in terms of moduli then, that's saying that the modulus of Z plus W is less than or equal to the modulus of Z plus the modulus of W. Now, I've said less than or equal to because there is a possibility of equality if that triangle in fact is flattened down to a straight line, if those 3 points are what we call collinear. We can also think in terms of subtraction. Clearly OA minus AB is going to be smaller than OB. So again, thinking in terms of moduli then, that means that the modulus of Z minus the modulus of W is less than or equal to the modulus of Z plus W. And putting those two results in terms of addition and subtraction together, we get the kind of generalized triangle inequality. Now you're going to see the triangle inequality crop up all over the place, not necessarily just in complex numbers, it can occur in other topics as well. So it's a rather useful result.